We're just gonna. Oh, we're gonna do God's fixed.
All right. Let me start off with the calendar. So we're not quite in September yet, so I just put both the calendars on half sheets here. So we're going to start off with limit definition of a derivative. We're going to spend 2 days on this. This is really for us to draw that connection between slope and derivatives, and that they're essentially the same thing. And then limits provides that bridge between slope and derivatives. So we're just going to see kind of conceptually that transition from algebra to calculus. But after we get through with that, we're not going to see much of it. We're going to have a much more efficient way to find what we call derivatives after Labor Day weekend. So just, bear with the fact that this is a little bit tedious, but it's really for the conceptual understanding of these concepts. AP exams do test over this, but it tests in a way where it's more like conceptual than actually working through it. So as we work through it, it's going to feel tedious, but just know that it's only temporary. We're going to have a much more efficient way of working through these slope formulas after when we come back next week. So next week we have derivatives and particle motion, and we're going to just kind of focus on these three topics to prepare for our quiz, which will be the following. So next week, no quiz, no assessment. The following week, we're going to have a quiz Thursday over power rule, particle motion, and product quotient rule. Okay, so this is really, when we get to this next week, this is really the foundation for what we're going to do the rest of the semester. So, but this is more of a conceptual that we're going to go through. Okay, so let's go to our notes. So let's start off with this. If I ask you to find the slope of a line, then all we need is what to find slope of a line? What information do we need? There's 2 points, right? Any 2 points. We do rise over run. We do change in y over change in x. And we have our slope. Is the slope ever going to change on this line? It's a static slope, right? If it's a slope of 2, it's going to be 2 all the way through from, yeah, no matter how far we are along this line, it's going to be the same slope. Okay. What if I ask you, what is the slope of this curve? Then you would say, well, it depends, right? If we're talking about this point, then that's a slope of maybe 3 or 4. If it's a slope here, that's slope 0. If it's over here, it's -3. If it's here, it's back to 0, right? So the slope is ever changing. But it follows a certain pattern. And what we're going to do is calculus is going to allow us to find a slope formula for this curve, right? Before, a slope formula is just a number, but now a slope formula is going to be for a graph that's ever changing. We're going to be able to find the exact steepness of every point on this curve. Right? So that's really the benefit we're going to see with calculus. So we're going to start with this, though. We're going to start with slope formula and see if we can build something that can help us get to a slope formula for an ever-changing or for a curve that where the slope is ever-changing. Okay, so we're going to kind of build it from something that we already know. Now, let's say here is our goal. Let's say our goal is to create the slope of this tangent line. So again, tangent line is a line that is going to skim the surface of the curve at a certain point, and the tangent line is going to share the same point as that curve and share the same slope as that point of tangency, right? At point P, that curve is going to be experiencing the same slope as this line. Okay, so that's what tangent means. Tangent, a line that skims the surface and also shares the same slope of the curve at that point. So let's say this is our goal. Our goal is to figure out a slope of this tangent line. But the issue with tangent line is that we can't pick 2 points on the curve that will have the exact same slope as this line, right? Because this line only shares 1 point with the curve. And if I want to pick 2 points on this curve, I can, I'm not going to be able to get the exact slope. But what if we start with this? What if we started with a secant line? So secant line is just a line that touches or crosses through 2 different points on the curve. Now we can definitely find the slope of the secant line because we can just find 2 points on this curve and just do slope, right? So we know the slope of the secant line. Like I said before, it's just change in y over the change in x. So the slope of the secant line is not a very good approximation of the slope of this tangent line, but it is some approximation, right? Maybe the slope of tangent line that we're after is 1/2, but right now we're sitting at a slope of 2. But is there anything that we can do so that our slope of our secant line can be improved upon? Yeah, let's just pick points closer on the curve towards point P. So if I pick points that are closer towards point P, you can kind of see what that could do, right? The slope of the secant line is going to start gradually coming down, like what I have this in this diagram. And it's going to continually improve upon getting closer to the slope of that tangent line as long as I pick points that's closer towards my source. And so if we kind of follow that idea, then it's like, well, if we can continue to get a better and better approximation, what if we can somehow pick points that are so close to point P, where that second point can just disappear into point P. And if it does, then we can technically achieve the slope of the tangent line. So that's where limits can come into play. We're going to use limits to allow us to decrease that distance between points P and Q until we start off with 2 points, but then we basically merge that second point into the first point, and we've achieved slope of the tangent line. And we use slope to begin with, and then we use limits to draw that second point in, and then technically we're going to be able to achieve slope using just 1 point. All right, so I'm going to help us build what that formula is going to look like. Okay, so we're going to use a lot of variables here because we want that flexibility to be able to move certain things about the points. If we just use static values, it's kind of stuck in place. So every point that we're finding is on the curve. Okay? So let's say point P is some x value distance away from the origin. And if I plug x into the function, then I can technically say that point P is just x f of x, right? F of x just represents the y value of a point on that curve for point P. So let's say point P is x comma f of x, just some random order pair, but it allows us that flexibility to be any point on the curve. Now, let's say we want to find a point that is some distance away from point P, which is point Q, and we know that point Q is going to be some distance away, and I'm going to call that distance h. So what do you think my x value would be if it's h distance away from x? Yeah, just simply x plus h, right? If this was 2 and this was 3, it'll be 2 plus 3, which is 5. If this was 1 and this was 7, it'll be 1 plus 7, which is 8. But we want that flexibility to be any point, so we're using a lot of variables here. So if we plug that x plus h into the function, then my order pair for point Q is going to be x plus h, my new x value. That's obviously some distance away from x. And if I plug that into the function, what would that look like in function notation? Not f of x, but good, f of x plus h. This means whatever new value that I find, if it's 5, 6, or 7, or 8, it gets plugged in as that new y value. So we know that f of x and f of x plus h will be different y values for different x values, right? Different order pairs. Okay, so we're simply going to just find slope using these variables. We want that flexibility to allow that h to move and to decrease. So that's why we're holding on to all these variables. Now, we're going to build our slope formula. So let me call this x1, y1. And let me call this x2, y2. And we're simply doing slope using all these variable function notations. So again, slope is simply change in y over the change in x. So I've labeled everything. So tell me what goes in the numerator if I just want to do change in y. What's y2 minus y1 for this particular, this set of order pairs? F of x plus h minus f of x all over minus x. Yep. So it looks messy, but it's really just slope, right? It really is just slope with function notations with a bunch of variables that are unresolved. So we said that we wanted to decrease that distance between x and x plus h, right? Because we want our secant line slope or secant slope to become more and more accurate. And if I can make that h approach 0, then I can get that second point to fall into the first point. And then technically we would have achieved slope at a single point. So we're going to say this. Limit as h approaches 0, we're going to decrease that distance between x and x plus h, or p and q, by decreasing that distance h. And then we're going to take that slope and draw that second point in and get better and better in slope as we decrease that distance. So f of x plus h minus f of x all over, and this reduces, right? Reduces to what? Just h. So this is what we call a general limit definition of a derivative. I'm going to call this f prime. So f prime is just a notation for a derivative function, and derivative is just a fancy word for slope. But this is more powerful than slope because slope is just static. But this is going to allow us to figure out the rate of change at any single point on that curve. So it's able to help us find, allow us to find information that we would otherwise be just doing approximation or taking a long time with just algebra to do, finding points that are really close to each other and dealing with a bunch of decimals. Okay, so we're going to be working with this, and we're going to be using this to kind of build these slope formulas for different graphs, right? Every curve has a different pattern. So every curve is going to have a different slope formula. And this is going to help us find that slope formula that's built specifically for a certain curve with its unique patterns. So whenever you see that f prime of x, that apostrophe, that just indicates that it's a derivative function. And again, derivative is just steepness of a curve at a single point. And our derivative function is going to be a slope finding formula for a curved graph where the slope of the curve is ever changing. There's also this alternate definition of a derivative, which we're also going to work with. You can tell that this kind of has that look of a slope. So we're going to work with both of these. Both of these, they essentially do the same thing with some slight changes, some slight adjustments. So, but today we're going to focus mainly on this general limit definition of derivative. Let's go to the next page, page 2. Hey, let's start off with the simplest function, a simplest curve function that we know, right? The simplest curve function that we know is x squared. We are very familiar with x squared. That's just a parabola that opens up, that hits a vertex order pair 0, 0. Right. So we're going to build our build a slope formula for this y equals x squared, for this fx equals x squared. Okay, so what we're going to do is we're going to try to insert our x squared into this limit definition. And we've been practicing with this, right? Even during our unit P, we were practicing with this limit notation. We didn't know what it meant. We didn't know what this meant, but we're just kind of going through the algebra so that when we get to this point, we can kind of just get through it. So if my f of x is x squared, right, I'm just replacing my numerator and getting it out of function notation. I can replace f of x with x squared, but I need to find a replacement for f of x plus h. So to do that, we know that f of x is x squared, and we want to find a new argument for x, which is x plus h. So if I put a reserved spot for my new argument, I can now insert that f of x plus h into my function. So now we're going to put everything into our f prime definition. So limit as h approaches 0. My f of x plus h has been built for this function, so it's just simply x plus h squared. Again, if you're doing f of x plus h, all you're doing is every x you see in the original function, just remove it, and then in place of it, put an x plus h. Minus f of x, which is x squared, all over h. So now this just feels like a limit problem that we've been working on since last unit. First things first, direct substitution, right? Replace every h with 0. What do we get? Numerator, we get, I replace h with 0. What I get in the numerator, which is 0. Denominator, we get 0. That tells us what? There's a hole, the limit exists, so we keep going. Okay. So we know that we're going to be trying to find an h in the numerator to cancel out. So we're going to FOIL all this out, clean all that up, get the h to cancel out, reevaluate the limit, and we should get something that is no longer 0 over 0. All right, so I'm going to FOIL all this out here. X plus h times x plus h. That's just going to be x squared plus 2xh plus h squared. All right, what can we do in the numerator? Yeah, x squared cancels out. And what can we do after that? We can factor out what? An h, yeah. H is canceled out. We're just left with 2x plus h. And then what's our final step? Yeah, replace any remaining h's with 0. So what are we left with? What's our remaining expression? Just what? This is 0. Are we replacing h with 0 or x with 0? H. So what's left? Good, just 2x, right? So we went through what we started off as slope formula, and we found the limit as h approaches 0. So we're decreasing that distance between those 2 points and until it approaches 0. And we went through all this process and we got this as a result. Normally, if we went through slope formula, changing y over changing x, you would get a number because we're just looking for a point. We're just looking for a slope between 2 points. But now we're picking 2 points on the curve and using that to figure out a slope formula. And what we got back in return is f prime equals 2x. So what that is telling us is that this is a slope formula that is built specifically for this y equals x squared. Okay. So that means that any point on this curve, if I plug in the x value, the location, in return, I'm going to get a number, and that number is going to correspond with the exact steepness of the curve at that point. So if you were looking at this curve and you're just making some ballpark estimations as to what you think the slope would be, I'm just picking a random point here. Okay, we don't even know what the x value is. But here, if you had to just give me a random slope, what could that slope be at this point? Would it be some negative number? Would it be 0? Would it be some positive number? Some negative number, right? Relatively steep. So what if we just say like -6? Okay. What's going to happen as I get closer towards 0? My slope is going to become what? Yeah, so give me a number. Yeah, -3, right? And then as I get closer, -1, what's going to happen here? What's the slope here? Yeah. And then it's going to be symmetry, right? So as long as I'm same distance away, I'm expecting 1, 3. I just want us to connect a curve with a slope number, right? Either positive, negative, or 0. And then obviously we can tell when something is steeper, you're going to get a larger number. And if it's not as steep, then that number will be closer to 0. So let's just play with that here. We expect this value to be 0, with that slope to be 0, right? So let's test it out and just convince ourselves that this actually does work. So f prime of 0, what's 2 times 0? 0. So that's consistent with what we see on the graph, right? The slope at this x value 0 is slope 0. Let me choose a point that's to the left. Let me choose f prime of -2. So maybe that's somewhere over here. If I plug -2 into the derivative, what do we get? -4. So that's we can be convinced of that, right? If we move to the left to 2 units, this looks like it's a negative slope. That's not too steep, but what if we move further away? Let's say f prime of -5. That could be further over here. Would you expect a steeper slope than f prime of -2? You would, right? Because you can imagine that curve is going to get steeper at further that we move away from the origin. So what's f prime of -5 going to give us? -10. Right? That's the exact steepness of this curve, y equals x squared at that point. Right? And likewise, if I move to the right side, f prime of 2, I would expect symmetry. Right? If I'm 2 units away, I should be expecting a +4, and I do get that. F prime of 2, plug 2 into x. 2 times 2 is 4. F prime of 5, 5 times 2 is 10. So every curve is going to look different. And so every curve is going to have its own slope formula, derivative function. You can see how powerful this is. This is, imagine if we only had slope formula to work with, then we're always be picking points close to each other. And the best that we can get after all that work is just an estimation. But this is telling us the exact steepness of a point on the curve. So part B, it says write the equation of the tangent line of the function at x equals 1. So now we're going to figure out what is the slope of this tangent line that we see here. So anytime we want to find the equation of the tangent line, and if we want to put it in the point slope form, all we need are 2 sets of information. We need order pair, and we need the slope. And we know the x value is 1. So how can I find the order pair? Plug 1 into what? How can I find the y value at a point on the curve? Plug into the f of x, right? This is my original function. So f of x, f of 1 will be 1 squared. So my order pair is just 1, 1. But now if I want to find the steepness of the curve at this point, I can plug 1 into what? To the derivative function, right? So what's f prime of 1 going to be equal to? 2 times 1, which is just 2. So my slope is 2. So the equation of this line here, this tangent line to the curve at x equals 1, is just y minus y sub 1 equals m times x minus x sub 1. So right now, the big thing that I want us to understand is that your function and derivative, they both talk about the same graph, right? But you can give both the same set of information, but in return, you're going to get something different. So if I give the function an x value, it's going to get me in return a location, right? Y value location on the curve. But if I give the f prime an x value, in return, it's going to tell me the steepness of the curve at that point. Okay. So right now we have to understand, between function and derivative, that they both talk about the same graph, but they give us different information. And so we have to know, okay, if I'm looking for slope, I need to use the derivative. If I'm looking for a location, I'm going to use the original function. So on the same curve, can we find the equation of a tangent line at x equals -5? So let's say -5 is over here. Can we gather enough information to create the tangent line for this? Find for the equation of the tangent line that's going to skim the surface of the graph at x equals -5. Okay, so try that. See if you can find the ordered pair using the function, find the derivative, or find the slope using the derivative, and then do point slope form. Same formula, just different points. Hey, what you guys get for your ordered pair? 525. What'd you get for your slope? Yeah. Just put it all together, right? My ordered pair is -525. Whoops. My slope is -10. And I just put into point slope form. And that's going to get me the equation of this line. Okay, any questions? Okay, so over the course of today and tomorrow, we're just going to practice using limit definition of a derivative. We're going to introduce different graphs, and then we're going to build the slope formula for that graph because every graph has a different pattern. So every graph is going to need a different slope formula. All right, let's go to page 3. Find the general. So for part A, we will do the general definition. And then for part B, for example 3, I'm going to talk about this alternate definition, which is similar but slightly different. Okay, so let's first build the general derivative. We know our function is square root of x. But we always want to get our function ready to be able to take in our new argument of x plus h. So I'm just purposely removing the x and reserving with a set of parentheses because that's where my x plus h is going to go. So now I'm just going to put everything into my limit definition. I've already found replacements for my numerator, and now it's just going to feel like a limit problem from unit 1. First things first, direct substitution. We know there's a hole. Go through our conjugate method to find a pair for that, get that H to appear, hopefully, in that numerator. Right, X's cancel out, and then the H's also cancel out. That's what we're going to be after. We're always targeting that H's to cancel out. There's a 1 left over, and then what's our final step? Yep, replace all the H's with 0. So our denominator is just left with root x plus root x, which is what? 2 root x. So this tells us that the slope formula for my radical function. So this is basically what my y equals root x looks like. It kind of looks like this, right? You can kind of tell that it's a pretty gradual slowing, growing function. So any x value that I plug in is going to be a positive number, but it's going to be a pretty small decimal value. And that kind of makes sense, right? You look at this graph here and kind of convince yourself that, okay, this graph doesn't, it starts off steep, but then it becomes less steep. And you can imagine the larger the number that you plug in, the less steep your curve will become. Okay, so part B, let's write the tangent line of the graph at x equals 2. So we're going to basically build what will be the tangent line equation, or equation of the tangent line that skims the surface of this curve at x equals 2. Okay, try that. You're going to find your order pair, find your slope. Remember, order pair comes from your original function. Your slope comes from your derivative. And then from there, put in the point slope form. And then we like to leave things in point slope form. It feels like it's incomplete, but you have information. You have enough information where you're going to get full credit. So, but if you wanted to, if you just feel like you want to get it into slope intercept form, that's fine as well. You won't have points taken off. You're just spending additional time on a problem that's already finished. So my function is root x. My derivative is 1 over 2 root x. If I plug 2 into the function, I'll get root 2. So that's my y value. My order pair is 2 comma root 2. If I plug 2 into the derivative, I'll get 1 over 2 root 2. That's my slope. And then point slope form, and that will get me the equation of this line that skims the surface of the curve at x equals 2. That makes sense. Any questions? For example 3, we're going to practice this other definition that you see to the right of the general definition. This is called the alternate definition, or the alternative limit definition of a derivative. The difference here with the alternate definition is that you know how this general definition, if I want to find the slope, it's a two-step process, right? We have to, this will first take us to the slope formula. And then if I plug in a number, I can find the slope. But that slope formula is very powerful. It can be used, once I have that formula, I can find it for any range of x values or any point on that curve. Very robust, right? But this potentially is a faster process, but it's going to skip the formula and it'll take you directly to just a number. So it's faster in the sense that it can get you to that slope value. But then if I want to find a slope at a different point, I got to start from scratch again, and I got to find this. So if it's just a one-time scenario, it's faster. But if you want to build something and you want to use it multiple times to find slope at different points, then you prefer going through this. Okay. But let's practice going through this alternate definition. Okay, first, I'm going to write out and we're going to find the exact same information as above. So we're going to find that the slope at 2 is going to be 1/2√2. But instead of going to the formula and then to the slope, it's going to take us directly to this number. So we already know what we're after. We're just going to practice that process. Okay, so here's the alternate definition. I'm going to have you guys write it down again. So you can see how we can build it the same way every time. So the first thing that we can do, and this will make things instantly more recognizable in terms of what we can do next. The first thing you're going to do is you're going to replace all your C values. What do you think the C value we're going to use for this problem? 2. Yeah, we're trying to find the slope at 2. So if you replace every C with 2, things will begin to take shape in terms of what we're going to do next. Now, just like our previous example, for our previous limit definition, our initial work is just trying to get the numerator out of function notation. Same thing here. We're just trying to get the numerator out of function notation. So we're just trying to find a replacement for that f of x. If I get that numerator out of function notation, then I can just go through my limit process and evaluate my limit like how I do in the first unit. What can I replace f of x with? Good, square root of x. What do you think I can replace f of 2 with? Just plug 2 into the function, right? What's f of 2? Just what? Root 2, yeah. So those are my 2 replacements. My f of x gets replaced with a function. My f of 2 gets replaced with root 2. So now it'll feel like a limit problem that you've seen from the previous unit. Okay. So go through your direct substitution step. Conjugate. All right, what do we see here? Do we see a matching pair? We'll cancel this out. Yep, but there's a what left over. One. Our final step. Replace the remaining x with 2. Do we get the same answer as above? Yes. This takes us directly to the slope. It bypasses the formula and takes us directly to the slope. It's faster for one-time use, but if you want to find the derivative multiple times for the same function, then the general definition is better because you can just get a formula and you can just reuse it for different points. Okay, tomorrow we're just going to practice through this. Nothing new tomorrow. We're just going to do the same things. If you guys can check your calendar, your homework is AP practice, so you may have to look a little further. So page 8, you're going to see that AP practice. All right, so that's your homework for tonight. I'll send out a reminder and I'll send you a link to the new unit page where you can find the solution key for this. All right, come get your phones.